Hello. It's been a hot second. So, people who follow me on Instagram know that I've been working on a new knife named Midnight. Such a fabulous name, I know. And I figured it was now time to start making videos on some of the processes to make said knife. I got 2 sold so far. I sold the second one this morning, so it's been going good as far as that goes. This knife has taken me a lot less time to go from like design to actually like to an actual product that I'm happy with, so that's been good compared to Iris. So that's fabulous, but the thing I've been dealing with recently, or probably forever, is like the actual finishes on the blades. Now, the handles and everything come off the machine like pretty good, and then like I'll usually just sand the handles and everything, and then tumble them or blast them, and then they're at an acceptable level of quality to be shipped essentially. But the problem with the blades is, and I have one right here, is you go through a lot of handwork to get the milled marks out, and I'm not sure I can see this on the viewfinder, but you can still see some straight milled marks in the blade in the finish, and this finish is essentially supposed to be kind of random. The problem with human eyeballs is we're pretty good at picking up patterns, it seems, and the way light hits things makes patterns show up pretty easy, I guess. So you can have like a really nice satin-like smoothed, sanded finish, and in certain light it won't show the milled marks, or it won't show a scratch or anything, and then in other lights it'll show this like deep scratch or something. So I've spent like many hours trying to figure out the best way to finish the blades, but yeah, so that's been like a real sticking point. It's like there's a lot of hand finishing involved in finishing the blades, which has been not frustrating, but just like very time consuming. Yeah, so, but in this video we're going to go from this piece of material. This is CPM 20CV, a very common steel at this point as far as high-end steels go. It's sort of equivalent to M390, and I say sort of because the chemical composition is slightly different, and I mean very slightly, and don't quote me on what the difference is, but there is a little bit of a difference. But CPM 20CV is essentially Crucible's version of M390, which I think is made by Bowler. Yeah, so we're gonna go from this blank to hopefully, I'm not sure how long the video is gonna go for, to a milled version of this with burrs and everything on it. So some people might want to see like what it takes to actually make a blade, and this should show like a good majority of what it takes to make, or at least mill, one of these blades. And it is a lot of steps compared to like the handles. Yeah, so I have one loaded, and we'll go over like the tool paths and stuff for people who are interested in that. And yeah, I think it should make a decent video. So let's go. So this knife has been primarily worked on the 4th axis. I've gotten comfortable with using the 4th axis, and so basically a lot of parts on the knife utilize this tombstone, and there's some indexing and stuff. There's no simultaneous toolpath stuff. One, because the finishes aren't that good simultaneous, and then Fusion doesn't really have great simultaneous toolpaths. There's really no need for simultaneous 4th axis work right now. So for the first operation for these knife blanks, this is a 5/32, which off the top of my head I don't know how thick that is, but the final blade thickness is 1/8, so 0.125. So what we're first going to do is we bandsaw cut this blank. This is 1.5 inches wide. I have some pit bowls that hold the blank in on the tombstone against the end here. I think these are only 0.2 thick, and there's only these 2 tabs at this point, or 3 tabs, 4 tabs, sorry, holding it material-wise. So you actually, for this step, the way I'm doing it, you don't need much material here clamping force-wise. There's this facing operation doesn't generate a lot of force, so I'm able to use just these 2 small pit bowls. We'll face it, and I'm going to drill 2 holes actually 4 holes. The 2 holes go above 2 tapped holes that are in the tombstone itself. And what we're going to do is we're going to pull the pit bulls, and then we're going to put the 2 tapped holes in, and then the 2 tapped holes are what hold the actual stock in to rough out the blank. And then what we'll do is we'll take that blank, and then we'll go heat treat it, and then after that it's all hard milled. But yeah, so yeah, let's go over the cam. It's pretty simple, pretty self-explanatory. This doesn't require any indexing. You could do this on a 3-axis fixture. Alright, here's op 1 on the tombstone. So first we're using a flat toolpath, and I'm driving the depth of the flat toolpath using another body, which is located below the top surface. The reason I'm taking material off the top is because, after heat treat, we're going to surface grind, and I don't want to have to surface grind whatever 5/32 is all the way down to 0.125, because that would take all year. So we're essentially facing the part down to a dimension that's closer to 125. I think it ends up being like 133 or 132, which is pretty repeatable. Yeah, you want to leave, I'm leaving like 7/8 thou, just because the process still isn't perfected, if you will, surface grinding wise. So if there's any warp or a really bad bow or something in the part after heat treat, you need enough material to actually be able to surface grind that warp or bow out. So that's why I'm kind of leaving a lot. In the future, I'd like to only be able to leave like 5 thou, because that would increase the surface grinding speed significantly. But anyways, the reason I'm using a flat toolpath as opposed to a facing toolpath is because I was using flat and using the pocket before, just because this is stainless. It's annealed and it's pretty soft, but still it's better for the cutter, I guess, to do this like engaged all the way type thing. But I found that when the cutter comes in and does its final pass, it's like rubbing on these last 2 passes. There's no material left, but the cutter is still actually touching the part, which is not really great in stainless, and it dulls the cutter pretty quick. So we're going to try this, where we're going to use parallel, which is essentially like a regular facing toolpath. Let's see. After that, 5 minutes of doing that, I'm using air too. I'll show you guys that though. I'm drilling the thumb slot out. I'm putting 2 drilled holes into it because it's pretty quick to drill material. And then what I'm doing is I'm drilling out these hold down stock tabs, and the stock tabs are for the later ops. That's to hold the blade down. And the reason you use a drill as opposed to using an end mill and boring is because drills take material out pretty fast. They're cheap, they're really cheap, and then you don't wear out your end mill prematurely. After that, I come in with a end mill and I actually widen out the hold down holes just slightly. I found that they tightened up a little bit too much when using bolts through them on the op 2, but you all see that. And yeah, so that's pretty simple, and that's the first part. Then the second part is, I'm not sure why these are ungenerated, but the second part is the pit bulls get pulled out, and in the future I'd rather have, the original intention was not to have to pull the pit bulls out of their little hole there. So they sit here. Like I said, the original intent was just to be able to clamp this down, loosen these, and then finish the rest of it. But I found to access the side of the part, I really needed the area where the pit bulls are. So in the next fixture that I design, whenever that'll be, I'll be sure to leave enough material around the pit bull so the cutter can come in and not have to touch the tips of the pit bulls when it's cutting. That way you don't have to fuss around and deal with actually pulling the pit bulls. It's kind of a pain. So for this quote, second operation, if you will, we put these 2 bolts in, and they're a little more narrow. Like I cut around them, so they're, I'm really sure we call them narrow-headed now. And then we take that first tool we faced with, and then we basically rough out the overall profile, and from there it's subsequent rust machining operations. Yep, do a final contour, and then there's a final rust adaptive, and then what's really important here is these two areas here. So this area against the, what do you call this, tang of the blade? Rear of the blade? This stop area right above the stop pin, or below the stop pin, and this area, they need to be pretty precise because they actually get located. That's what I'm using to locate the stock after surface grinding and heat treat and surface grind, back to the fixture on these dowel pins. So that's this. So this is essentially a 3/16 hole. That's obviously half. And then this is a 3/16 hole. So I put dowel pins here, and then you basically rest the blade up against here, and then tighten all your, your hold down holes. The reason there's a gap right here is because I'm actually leaving 15 thousandths on the entire outside, and the reason you leave 15 thousandths is because it can grow or shrink during heat treat, and you need material to cut away. So I figured 15 thousandths was enough. Some people leave like a lot more, like 100 thousandths. I thought that was like a lot of material to have to hard mill. So I said I'll give 15 thousandths a shot, and it seems to be working really good. And actually, this 3/16 hole doesn't have a noticeable change in dimension to where relocating it back to the fixture is a problem. The reason it doesn't need to be super accurate, and the reason I'm able to do this, is because none of the critical blade features are actually cut at this point. That all happens in this first operation, so it doesn't really matter if it doesn't locate correctly as long as it locates within that 15 thou outer buffer. And that's it. So now let's get to cutting. So as you can see, I'm using air blast. So supposedly, and I don't have enough tool longevity data to prove this to myself, but air blast is better with like Altin coated tools, so the coating on the tool gets activated from the heat coming off the chips. And this supposedly reduces that like cold fracturing that cutters can experience when you have a hot cutter and then cold coolant hits the cutting edges. So yeah, so that's why I'm using air blast. The only issue with air blast is essentially generating air is pretty expensive electricity wise and maintenance wise for the air compressor. But yeah, at least you guys can see better. So it's gonna do this for like 5 minutes, and then we're gonna drill some of those holes, and then we'll do the roughing. So while that's cutting, we're gonna fire up the heat treating furnace because it takes absolutely forever to heat treat things, believe it or not. So this is a Paragon heat treating furnace. It's brand new. I've only used it like 20 times now for these new blades, and yeah, it was not cheap whatsoever. So for the blades, I'm going to what is it? Because I'm not doing cryogen right now. 2050 is the temperature I'm going to, with a plate quench, and then 400 degrees tempering, and I'm holding it on the plate for 15 seconds for a first blade, and then, 18 seconds for a first blade. Wait a minute, 15 seconds? We'll just say 15 seconds, like count out loud, hold it down, 15 seconds. That's actually cold enough for me to handle the pouch that the blade is in, believe it or not. And then it goes in there, and yeah, supposedly after a quench, you really don't want it to be like room temp. It needs to be like 100 degrees. It's like 150 or something. So I figure 15 seconds is probably a good time. I don't have enough data to say what is good or not, so yeah, like over time things get better, and this is so far what I've found to work quite well. So for this thing, obviously we're not going to go over programming this, but it's a pretty good unit. My only issue is it's very slow. It runs on 120. You got to have a dedicated outlet for it. At least the manual says that. And it basically takes 2 hours to get all the way up to 2050. And another kind of annoying issue with this thing is this RA thing is basically how fast it'll ramp in degrees. So when it says full, it actually means it's going to pull as much power as possible and essentially heat the oven as fast as possible. When you get up like over 1500 degrees, you can't use full, because what happens is it's commanding a certain like degree per minute rate, and if the controller can't reach that because like the internals, like it's not keeping up, it basically throws an error and it says failed to heat, and then it just stops heating. Like it just gives up. So I don't know, it's kind of frustrating because I figured out like the correct ramp amount, if you will, to get it to not do that. But the issue is, let's say I'm at 1500 degrees and I haven't put the blades in. Well, I open the door and then put the blades in, and then I shut the door. Something about the cold air reducing the chamber temperature and then the controller seeing that and then trying to ramp up sometimes causes it to fail to heat as well, which is like super frustrating because of, like I said, how long it takes to heat. So that's my only real gripe with the unit. But other than that, it's like a really well-built unit, and this one's also really big. I think it's 24 inches deep on this one, which is, you know, it's pretty long for what I'm using it for. But anyways, so yeah, other than that, it's been good to me. So it's drilling those holes now, and those are just clearance holes for the bolts. And I'm using high-speed steel because I'm cheap and I can't afford carbide right now. But hopefully soon. Okay, then this cutter comes in and widens out those holes. Sweet. So since I'm doing 2 blades, I'm doing it again. I just find it easier to run the first operation twice, because like I said, I just swap those pit bulls out, and this just saves a couple extra steps. The nice thing is locating the cap holes, or the board holes, doesn't need to be very accurate, because we're still in the roughing stage. So yeah, like what'll happen now is I'm only going to use these 2 bolts to locate and hold our stock down, and then it's going to do all that roughing. Alright, so we got our 2 pieces of stock all finished up. Even pulled the sticker off for me. How nice of the machine. Probably should have scraped that off, but anyways. So now this is the op 2, if you will. So I pulled the pit bulls out of their slots, and we put our 2 reduced head bolts. And you can just reduce heads like this by literally running a contour toolpath around them. Pretty easy. So they're like this, so I can get by them with a tiny tool that's got kind of a short shoulder. And yeah, so this is, I found I only need these 2, I think they're 8/32 thread. You only need that amount of holding force to hold this and actually rough it out. So we're back to our 1/4 inch 8 flute cutter. And you can go pretty quick when the steel is in its annealed condition. So essentially we're removing as much material as we can with this large cutter, and then we're going to come in with a 1/8 tool after this and rest machine all the way down until we have 15 thou on the entire outside of our part. Here's our 1/8 cutter. So this is a corner radius stub length 1/8 cutter with Alton coating. And you can actually feed it pretty quick, which is pretty cool. This one does sound pretty dull though. Here's that pretty tiny cutter. I can't remember what size it is off the top of my head, but yeah. This is a cutter with a 1/4 inch flute length, which I have found to be not very rigid, so I would like to go to like a stub length of this cutter in the future, but for now this works. It took me quite a long time to get these couple tool paths to work reliably without the cutters always breaking, so yeah, stainless is a pain. Even more so of a pain compared to like titanium in my mind. Okay, so this is it roughed out. This is what we're left with. The only issue I ever have with this is the edges are pretty sharp. And I guess I could come in here and chamfer these edges, but you still have the bottom side. That just like makes making the foil for heat treating a little bit of a pain, but I usually just hit it up on like the polishing or the deburring wheel just to break the sharp edges. So before I remove it from the machine, I just make sure that a dowel pin will actually fit in here, and it does. You'll notice that the fixture has a little dip in it here, so a pin actually fits. So that fits, and then so that means when I go to, after surface grinding everything, it'll actually locate on these two pins properly. And yeah, that's it. So I'm going to cut the next one, and then we'll go and do the heat treat stuff. Alright, so this is what we got off the machine. This is still in its soft condition. I deburred the edges. The reason I deburr the edges is because we have to make these stainless foil packets that surround the blades, because you can't heat treat this type of stainless up to the temperature that we are without it being sealed away from oxygen. And don't ask me why, but it basically destroys the stainless. So yes, I was buying pre-made foil packs for McMaster, but that's kind of expensive, and I have some foil, like rolled foil, stainless foil already that we can just use to make our own. So this is what this looks like. This is 2,000 thick stainless foil. That's where I get it, Jantz, and then there's the number if you're curious. So I just cut it with regular scissors. Now, I have found that you want to be careful and not have creases, like an excess amount of creases, and 2 folds towards the last fold seems to be the best way. And then another thing is, I'm using this old surface grinding vise. It's got really, really sharp edges. That seems to be the best way to like get these things to seal, is really sharp edges. So first I'm going to fold it over in the center like this, and just hold one corner, and then I'll just run my finger like this until you get a nice tight seam there. And then I'll do the long ways. So run it up against this, and then basically pinch it against that corner. And then you got that. You can fold this over the last little bit like this, and then I'll take, this is a piece of aluminum, you can use anything, and I'll just kind of run it so it's really flat along the seam. So that's our first long fold. Then what I'll do is I'll do one of the bottom ones, and do this bottom. Same thing, nice and tight on the sharp corner. Bring that over like that. grab your thing to flatten it. Like that. So now we have one fold per side, and then I'll do one more fold. And you want to make sure, like what I'll do is I'll go in the same direction, but basically one after another. I won't do two the same side together, so they're kind of overlapping. And that seems to be, gets me pretty consistent results. Sometimes the bag doesn't work completely, and you'll get one end has some oxygen on it. But usually it's not enough to scrap the blade, which is a good thing. And I haven't had any issues with an uneven heat treat either, even if that does happen, that I've noticed anyways. So last fold on the bottom. And then these gloves, they're just like anti-cut gloves or whatever, you know, Chinese special. I just bought them on Amazon. And they seem to work pretty good because this stainless is really, really sharp. So now we have our little foil pouch, and what I'll do is I'll open it and try not to over crease it or anything. The less creases, the better the quench comes out, because the creases don't get in the way of the two flat plates. Some baby powder, like a really tiny amount, just keeps the blade from sticking, because I've found sometimes the blade sticks to the packet. But even so, usually it's not too big of a deal to unstick it. And then take our blade, and then I go tip down because the sharpened area is the most critical part. Bring that like that, and see, this one's a little bit long, but that's okay. And then same thing, two folds, and then, like I said, all my folds go towards the same direction, and in this case, like towards center. And one more fold. Cool. So this is a done packet, all sealed up. And see, I got as minimal amount of creasing along the top and bottom surfaces of the blade. That way when we go to pull it out and actually press it on those plates, hopefully there won't be any ripples or anything that get in the way of the actual quenching. So I'm going to do the other one, and then we'll throw them in the furnace, and that'll be that until they're done, obviously, being hot. Alright, so I got you guys on the lathe chip conveyor. If the camera falls from up there, it's going to break and it's going to be very expensive. So here we are at the furnace. Probably put your gloves on because it's warm. So typically when I do this, it'll do like a fail to heat error, like I was talking about earlier, but we shall find out. So let's see, let's be strategic about this. This is the flap area with no blade, so I'm going to pinch it here. Put it basically as deep as I can get it into the furnace without having like accessibility issues, because the longer you wait with the door open when you go to quench, it's actually quenching in the air as you do that, so the quicker you can get to quench, the harder it's going to be essentially. So stick it in here. We're going to go with this side one here. How to break these little ceramic rods in here. They're super easy to break. So there's that one. And here is the next one. And you want them laying vertically if you can get them, because that would be a more even heat treat, supposedly. Just going off internet data, so yeah. So that'll go to 2050, and based on the chart with a plate quench and then a 400 degree tempering, that should be right around 61 to 62 Rockwell C. And yeah, so we'll come back when this is ready to be quenched, and then we'll do that, and then we'll go to tempering, which takes a very long time. This is what I was talking about. So then essentially I have to abort the entire thing and then restart it at that segment, which is super annoying. Alright, we've made it at the part where I pull these out. So, I'm going to have to burn ourselves. I don't know how much you guys are going to be able to see with my back being here, but I'm going to pull one out. I'm going to shut the door so we don't air quench the other one, and then I'm going to press and quench one, throw it in the tempering oven, and then we're going to wait for this to get back to 2050, and then we'll pull the last blade out and repeat the process. Wait for this to get back to 2050. Okay. Then those get cooked for 2 hours at 400. So it took basically 3 hours to get from the cold oven, actually it was more like 3.5, all the way up to actually being able to quench the blade. So you can see it takes a while. And then tempering takes an additional 2 hours. So the blades take a really long time. Alright, cool. Thanks for watching. I'm going to actually cut this short just because I realized that if I want to show surface grinding and hard milling, both of those are going to take like at least, they'll probably be like an hour-long video if I do them together. So surface grinding might actually be its own video too. And yeah, so I didn't want this one to be really long, so yeah, I'm going to cut this one here. But thanks for watching. If you're interested, I'll put a link to these knives in the description. I cannot promise any are available, so because I'm making one like every 4 days it seems. So yeah, I will do like book spots at some point, but for now, yeah, they're kind of first come, first serve. I don't want to make any promises. And yeah, if you want to see more of this stuff, subscribe, and you can follow me on my personal Instagram. It's the same username as here on YouTube. And yeah, I post kind of day-to-day stuff on stories, so if you're kind of interested in that stuff, you know, follow me there. Alright, cool, and have a good one.